One of the most exciting topics in geometry is always circles, and one of the first things we study when we talk about circles is how circles and tangents relate to each other. If you have a circle and you have a tangent line, which is a line that touches it in one point and only one point, doesn't pass through the circle at all, it just touches the circle itself in one exact point. They have one point in common or one point of intersection. Anyway, that's a tangent. This is called the point of tangency. Because that's the point at which it's tangent. So this line is a tangent line to my circle, and I'm going to call my circle circle K. So circle K has a center, and we have a point of tangency. The point of tangency is on the circle. Anytime you connect a center of a circle to a point on the circle, you have a what? You have a radius. So that segment is a radius. So one of the cool things about tangents and circles, and this is actually a theorem, says that anytime you have a tangent, it is going to be perpendicular to the radius at the point of tangency. So the radius at the point of tangency means the radius that I draw from the center to the point of tangency. These are perpendicular. That's a right angle. And there's so much that can come out of that, because once we have a right angle, we could have a right triangle if we connect this or this way. And with right triangles, there are all kinds of things you can do, like Pythagorean Theorem or sine, cosine, tangent, or other stuff. So that's a very significant fact then. And you don't have to see this symbol for it to be true. It's automatically true. If you have a tangent, a line that touches the circle in one point, then it is definitely making a 90-degree angle with that radius at that point where it touches the circle. Now, a couple things you'll be asked to do with this. Sometimes you're asked to use this to verify whether or not you have a tangent, because remember, in geometry, you can't tell something just from looking at it. You can't just say, oh yeah, that looks like it touches in one point. Because what is one point? I mean, one point is like infinitesimally small. So, I mean, how can you tell it doesn't touch in 3 points? You can't. So, if I have something like this, and notice there's no right angle symbol, and it says, okay, this is 5, and this is 10, and this whole length is 13. Let's go ahead and give these some letters. How about A, B, C? And it'll ask me something like, is BC tangent to circle A? The way I know is, if it was a tangent, then this would be a right angle. Even if it's not shown, it still could be. So I'm going to use the Pythagorean theorem to check it, because if that's a right angle, Pythagorean theorem should work. So 5 squared plus 10 squared, and the question becomes, does that equal 13 squared? Well, this is 25, this is 100, and this is 169. That's a no. It does not equal that. So no, BC is not tangent to circle A. So it's not about whether or not it looks tangent. It's about, if these lengths are true, does that mean it's a tangent? Does that mean this is a right angle? Another way you could see it written, and remember, anytime I erase something, that's not a big deal. You can go back on a video, any place you want to go. What if it's something like this? I'm going to say this is 24, and this is 7. And this is 18. Now remember that with geometric figures, usually where we write the measurement on a segment is in the center. So if this is written in the center here, that implies that it's only from here to here. So that's going from B to the circle. Okay? So how am I supposed to do the Pythagorean theorem, or check the Pythagorean theorem? We're really doing the Pythagorean converse. If I don't know how far this is. Well, I do. Remember that if you know the length of one radius, you know the length of every radius, because every radius is the same. So if this is 7, this is 7. So what we're asking is, does 7 squared plus 24 squared equal, and let's see, that's 18 plus 7 squared. 18 plus 7 is 25. And it just so happens that 7, 24, 25 is a Pythagorean triple, meaning 3 whole numbers that make the Pythagorean theorem, or that fit the Pythagorean theorem. In other words, this is 49 and 576, and that does equal 625, and those are all whole numbers. So yes, it is a tangent because I just proved that that's a right angle by the fact that it fits the Pythagorean theorem. The Pythagorean theorem works for those numbers. All right, another question you might be asked is you might be asked to find a missing length using that fact that it's a tangent, or excuse me, the fact that the tangent is perpendicular to the radius. So let's say you have something like this. Okay, so if you were told this was a tangent, and you would pretty much have to be here because you can't tell because you don't know what x is. So let's say you're told that MN is a tangent segment, or maybe it's on a bigger line and you're told that that line is a tangent, and that this is circle P. All right, well then we know that this squared plus this squared should equal this whole thing squared. Leg squared plus leg squared equals hypotenuse squared. This whole thing we have to figure out how to write. This is x, this is 8. Do not multiply them. For some reason, a lot of times, if I were to put a 3 here, people would say, okay, the whole thing is 11 with no problem. Well, how did you get 11? You added 8 plus 3. But for some reason, when we put a variable in there, a lot of us want to say 8x. That's not 8x. That's x plus 8, or 8 plus x. Okay, so that's what that whole length is. So the length of Pn, which is the hypotenuse, is x plus 8. So my Pythagorean theorem then becomes x squared plus 12 squared equals x plus 8 quantity squared. This whole thing is squared. Now remember, if you square a binomial, it is not the same as just squaring x plus squaring 8. This is not going to give you x squared plus 8 squared. What it is going to give you is x plus 8 times x plus 8, and we FOIL. So x squared plus 8x plus 8x plus 64. So this is x squared plus 16x plus 64. And over here we have x squared plus 144. The nice thing about this problem is we have an x squared on both sides. If we subtract it from both sides, no more x squared. So it's not quadratic anymore. Then we can subtract 64 from both sides and get 80 equals 16x. Divide both sides by 16, and x is 5. All right, so that is a couple of the ways that we might use the first theorem about tangents and circles, which says that a tangent is always perpendicular to the radius at the point of tangency. There is another theorem about circles and tangents that I like to consider the ice cream cone theorem. It says if you have an external point or an exterior point and you draw a tangent segment from that to the circle, in other words, a segment that touches the circle in one place only, okay, and then you draw another tangent, which would mean it'd have to be on the other side of the circle, touches the circle in one place only. You see how that kind of looks like an ice cream cone? There's my ice cream cone. Well, the two sides of the ice cream cone have to be the same, or else the ice cream was going to fall off on the ground. Now, this one is being held sideways, so it's going to fall anyway. But the point is, this is a tangent segment, this is a tangent segment. They are going to be congruent. That's what the theorem says, that they will always be congruent. So, for instance, if you had, this is 2, let's say this is 6x minus 3. Let's do that. And this is 15. Well, then you're going to say 6x minus 3 has to equal 15. Add 3 to both sides. 6x is 18, and x is 3. All right, let's try a different one. Let's say we had one that looks more like ice cream. and this side is 2x squared, and this side is 18. Well, then 2x squared has to equal 18. Divide both sides by 2. X squared is 9. And x, in this case, it could be positive or negative 3. Because 3 squared is 9, and negative 3 is squared is 9. A lot of times in geometry, we would say, oh, you only want the positive one because you can't have negative lengths. But none of these are saying that x would be negative length. 3 or negative 3 would work here, because when you plug in negative 3 squared is 9, 2 times 9 is 18, so it still works. All right, last thing I want to show you about this same theorem, the one that says, the ice cream cone theorem, that says the two tangents from the same exterior point are congruent, is that if I have what's called a circle inscribed in another figure, or really another figure circumscribed about a circle. Let's say that the circle is an inscribed circle. So let's say we have a triangle. Okay. Let me draw this. There we go. So I have a circle inside a triangle, and it's in there in such a way that there's one point touching on each side of the triangle. Okay, that's called, that circle is inscribed in the triangle, or written in or drawn within. Okay, so here's the deal. Basically, in a situation like this, well, let me show you what it'll be asked. The way it'll be asked will be something like this. Let's call this A, B, C, and it'll say find the perimeter of ABC. And you're thinking, well, that would be wonderful to do if I had some more information, but I don't. But you do. Okay? So really what you have here is you have 3 ice cream cones. We have one here, we have one here, and we have one here. Okay, so in other words, this 4 here from A to this point, let's call it Q, has to be the same as from A to R. That's the ice cream cone theorem at work. Here's an exterior point C. 2 tangents from the same exterior point will be congruent. So the 7 here from C to Q has to be the same as C to S. So that's 7. And B to S has to be the same as B to R. So that's 12. So now all I have to do is add up all my sides, and I've got my perimeter. So 8 plus 24 is 32. Plus 14 is 46, and my perimeter is 46, whatever my units are. And that's pretty much the main stuff we ever look at, or the most of the stuff we ever look at when we have circles and we are talking about their relationship to their tangents.